Relative motion helps us determine how the motion of an object changes when it's viewed from a moving reference frame. For example, suppose there are two observers, A and B, watching a moving particle P from their own reference frames. Reference frame B is moving at a constant velocity, VBA, relative to A, as you can see in this diagram right here. This diagram includes multiple vectors, so let's go ahead and label what exactly each vector represents. For starters, RPA, this vector that we see right here, that's the position vector R of P relative to A. Again, remember that P is our particle, A is one of our reference frames. So then RPB would be the position vector of P relative to B. And finally, RBA would be that position vector of B, one of the reference frames, the moving reference frame, relative to A, which is our stationary reference frame. So, you'll notice that these three vectors make a triangle, and specifically, I can add these vectors together. Remember that when we add vectors, we put them tip to tail. So I'll notice that RBA and RPB, they're tip to tail. And when I add those two vectors together, I get the vector RBA. So I can find the position vector of my object relative to the stationary reference frame by adding together the position vector of the reference frame, of the object relative to the moving reference frame, plus the position vector of the moving reference frame relative to the stationary reference frame. And specifically, it's the position vector of the origin of reference frame B relative to A. Now, we know that velocity can be calculated based on the position vector. Specifically, we know that velocity is dr dt, which means I could take the derivative of each of these quantities to find the velocity of P relative to A. I would take the derivative of RPB with respect to dt, and in that case, I would get the velocity of PB. Same thing would happen when I would take the derivative of RBA. I'd get the velocity, BA. So I can calculate those relative velocities as well. One other thing to point out is that I could calculate accelerations as well. Acceleration is the derivative of velocity, meaning that the acceleration of my object relative to reference frame A is the acceleration of my object relative to reference frame B plus the acceleration of reference frame B relative to A. But I want to point something out. From the start of this video, it says that reference frame B is moving at a constant velocity. We know constant velocity means acceleration is 0. Therefore, the acceleration of my object is the exact same regardless of which reference frame I'm looking in. That's really important. When you're dealing with relative motion, we're always dealing with reference frames that are moving at constant velocities, so the acceleration is going to be the same there.